Ever stop to think about that screen you're looking at right now? Or the one you're probably holding? It's amazing technology, but uh, I've always been curious about how much energy actually goes into keeping those screens, so bright and vibrant.
It's a question that scientists have actually been wrestling with for decades. It's all about efficiency in the world of semiconductors, and the real kicker is that a big part of the answer has been staring us right in the face.
You mean like right in front of our eyes, like on those very screens?
Yeah, kind of. More like right in the blueprint of nature itself.
Okay, now that's intriguing. I love it when we can like tap into nature's secrets for our technology. So where do we even begin with this one? What's the problem with our current screens? Like at the fundamental level?
Well, for a long time, scientists have known there's this inherent structural issue with semiconductors. Their symmetry, or rather the way they're typically structured, symmetrical, it means a big chunk of energy just gets wasted when they produce light.
Wasted. Like how much are we talking here?
A significant amount. Imagine like half the energy you're using to power your phone screen is basically just disappearing.
Whoa, seriously. Half. That's a lot. So is that what we're diving into today? Figuring out how to recapture all that lost energy?
Exactly. Today, we're looking at a real breakthrough that tackles this problem head on. A team from the University of Cambridge and Eindhoven University of Technology have figured out a way to make screens way more efficient. And they did it by borrowing a page from nature's playbook, you could say.
Now we're talking. This is what I love about these deep dives. So what's the secret ingredient, the nature-inspired twist?
It all comes down to a concept called chirality.
Chirality. Okay, that sounds a little intimidating. Can you break that down for us? What does it even mean?
Sure. Think about your hands. Your left and right hands, they're mirror images of each other, right?
Yeah, of course.
But no matter how you twist and turn them, they'll never perfectly overlap. That's chirality in a nutshell. It's that property of handedness.
Hmm.
And it turns out a lot of molecules in nature have this kind of left or right-handed structure.
Huh. Never thought about it like that. So what does that have to do with our screens?
Well, that handedness, that chirality, it plays a crucial role in tons of natural processes, from like how DNA forms to how our bodies process food. Chirality is everywhere. And these researchers, they realized they could use the same concept to fundamentally change how semiconductors emit light.
Okay, I'm starting to see where this is going. So if nature's using chirality all over the place, why has it been so hard to like build that into our electronics?
That's the million-dollar question. Getting
Yeah.
materials to have this kind of specific handedness, especially at the nanoscale, where we're dealing with things 1,000 times smaller than a human hair, it's incredibly tricky.
Yeah, I can imagine. So how did these researchers crack the code? What was their big aha moment?
They found a way to design molecules that essentially self-assemble into spiral shapes. Like, imagine tiny little building blocks that naturally twist into either a right-handed or left-handed spiral as they come together. And they used a specific molecule called triazotroxine, TAT for short.
That got it. So these tap molecules are like tiny little spiral factories.
Mhm.
Okay, how does that help with the whole wasted energy thing?
It's all about how this spiraling structure affects the movement of electrons. When these tap molecules stack up in this helical shape, any electrons moving through the material are forced to follow that spiral path, too. It's like they're running along the threads of a screw.
Ah, I see. So they're not just moving in any random direction anymore. They're being guided along this spiral.
Yeah.
What does that do to the light they emit?
This is where it gets really cool. When electrons spiral like this, they naturally produce something called circularly polarized light.
Okay, another new term. Circularly polarized light. Hit me with it. What's so special about this kind of light?
Imagine normal light, like from a light bulb. The light waves are vibrating in every direction. It's chaos. But with circularly polarized light, the waves are rotating, either clockwise or counterclockwise, as they travel.
Almost like the light itself has a spin.
Exactly. It's like a tiny little corkscrew of light. And the direction it spins, clockwise or counterclockwise, depends on whether the electrons are spiraling right or left. So that handedness of the structure we talked about earlier.
Okay, now we're tying it all back together.
Yeah.
I like it. But why is this such a big deal for our screens?
Because this circularly polarized light is already pre-sorted,
Mhm.
so to speak. Remember how I said our screens use filters to block out all the light that's not vibrating in the right
Yeah,
direction?
that was wasting all that energy.
Right. Well, with circularly polarized light, you don't need those filters anymore. The light coming from the semiconductor is already aligned with what the screen needs, so you're not throwing away half the energy just to get the picture you want.
Wow, so all that wasted energy just disappears. That's pretty incredible. And I remember reading that when they shine some light on these tap materials, they produced a very specific color too, right?
Yeah, when they exposed the tat to blue or ultraviolet light, it emitted a bright, vivid green light. And this green light had a really strong circular polarization, something that has been really hard to achieve in semiconductors before now.
So it's not just efficient, it's also like super bright and vivid. That's pretty cool. And I think one of the researchers, Marco Prus, had a great way of explaining how this all works, right? Something about the structure being key to the light emission.
He said the structure of tat allows electrons to move efficiently while affecting how light is emitted. Basically, the way these molecules are arranged, that chirality, it directly determines the properties of the light they give off.
It's like just by tweaking the structure at this tiny microscopic level, they completely change the game. But okay, we've got this amazing material that emits super efficient, circularly polarized light. How do we actually use that to improve the screens we use every day?
This is where it gets really exciting for everyone with a phone or a TV. This breakthrough is perfect for something called OLED technology, organic light-emitting diodes.
OLED. I've heard that term thrown around, but honestly, I'm not totally sure what it means.
Think of it like this. OLEDs are a type of display tech that uses organic materials, like this tat stuff, to create light. They're known for having amazing color and pretty good energy efficiency already, which is why they're in so many of our devices these days.
Right, so how does our chiral material make OLEDs even better?
By eliminating the need for those energy-wasting filters we talked about, since the light coming from our chiral semiconductor is already circularly polarized, an OLED screen built with this material wouldn't need those filters anymore.
So our screens would use way less battery and be even brighter. That's a win-win.
Exactly. And the best part is, the researchers didn't just stop at making the material, they actually went ahead and built working circularly polarized OLEDs, CP-OLEDs, using this tat stuff.
No way.
Oh.
So they actually made working screens with it. What were the results like?
Let's just say they blew the previous records out of the water. These CP-OLEDs had the highest efficiency, brightness, and polarization levels ever recorded. Another researcher, Rituparna Chowdhury, summed it up pretty well. He said, "We've essentially reworked the standard recipe for making OLEDs, like the ones in our smartphones, allowing us to trap a chiral structure within a stable matrix. This provides a practical way to create circularly polarized LEDs, something that has long eluded the field."
That's incredible. So brighter screens, longer battery life.
Yeah.
And it's all thanks to a little molecular twist. But I remember reading that this chirality stuff, it has potential beyond just displays, right?
Oh yeah, this is just the tip of the iceberg. The ability to control the spin of electrons using these chiral materials, it opens up a whole new world of possibilities.
Like what? Give us a sneak peek.
Think about how our computers work now. They store information using the charge of electrons, whether they're on or off.
Right, the basic building blocks of digital information.
Well, imagine if we could also use the spin of electrons to store and process data. Electrons can spin, kind of like a tiny little compass needle pointing up or down. And if we can control that spin, we can create computers that are way faster, way more energy efficient, and even more secure than the ones we use today. That's the promise of something called spintronics.
Spintronics. I'm getting like sci-fi vibes here. So how does our chiral material fit into all of this?
It gives us a level of control over electron spin that we just didn't have before. So it could be a key ingredient for building these futuristic spintronic devices.
So we could be looking at a total reinvention of how computers work.
Huh.
That's pretty mind-blowing. And it all goes back to this tiny little twist in the structure of these molecules.
That's the power of fundamental research. And this discovery could have implications for even more advanced technologies like quantum computing, which, well, that's a whole other rabbit hole for another deep dive.
Yeah, let's save that for another day. But you mentioned fundamental research. This wasn't just a random discovery, was it?
Not at all. This breakthrough is the culmination of decades of work by two amazing research groups, one led by Professor Sir Richard Friend at Cambridge, and the other by Professor Bert Meijer at Eindhoven University of Technology. They've been collaborating for years, building on each other's work.
That's what I love about science. It's this constant collaborative effort building upon what others have done before.
Absolutely. And Professor Meisner really drove home the significance of this achievement. He said, and I quote, "This is a real breakthrough in making a chiral semiconductor. By carefully designing the molecular structure, we've coupled the chirality of the structure to the motion of the electrons, and that's never been done at this level before."
I think that quote really captures the essence of this whole thing. By understanding something so fundamental, the structure of these molecules, they've opened up a world of possibilities. And considering that the organic semiconductor industry is already worth billions of dollars, this could have a massive impact, right?
Definitely. The industry is already valued at over $60 billion. Any technology that can significantly boost efficiency and unlock totally new capabilities like this, it's bound to shake things up big time.
Okay, so let's do a quick recap of our deep dive today. We started with this problem of energy waste in regular semiconductors and how their symmetrical structure leads to all this light and therefore energy being lost. Then we learned how scientists took inspiration from nature's chiral structures and designed these incredible molecules that basically self-assemble into these tiny little spirals.
And that spiraling structure, it forces the electrons to move in a spiral too, which causes them to emit this special kind of light called circularly polarized light.
And that circularly polarized light is a game changer for OLED screens because it eliminates the need for those power-hungry filters, leading to brighter screens and longer battery life for all of us.
Plus, this breakthrough could be huge for other fields like spintronics and even quantum computing. It's amazing how such a seemingly abstract concept, this molecular chirality, can have such tangible and wide-reaching consequences for the technology we use every single day.
It really makes you wonder what other scientific mysteries are out there just waiting to be solved and what kind of crazy technologies they might lead to.
It's exciting to think about.
If you enjoyed this deep dive into the world of chiral semiconductors, be sure to like and subscribe and drop a comment below, letting us know what other scientific breakthroughs you'd like us to explore in future episodes.
We're always looking for new and fascinating topics to dive into.
Stay tuned for more insightful deep dives into the ever-evolving world of science and technology.